So last time I said the exponential distribution function looks like this. And that thing had something called the memoryless property, which means knowing that something happened before is not going to let you know what's going to happen later. Right? All right. So let's try to calculate the expectation value for this thing, which is, and this is on expectation value would be you integrate from 0 to infinity of x times e to the lambda x dx, and then you have to use integration by parts for this, but my favorite is to use tabular instead of integration by parts. You can use just regular integration by parts. If you haven't seen tabular, it's a really sleek method in doing the integration by parts. On my YouTube channel, I have several videos explaining the tabular integration in full. So if you have time, please try to review those. Yes?
Are we integrating lambda e to the negative lambda x, or xe to the lambda
Oh,
x?
thank you. Okay, so I should put minus here. I'll put that negative lambda here. So I put plus, minus. Well, there's one column where you differentiate, one column where you integrate. You differentiate until you hit 0. And then this column goes plus, minus, plus. Always start from plus. This one you keep integrating. So antiderivative is e to the negative lambda x. You integrate this one more time, you get 1 over lambda times e to the negative lambda x. Is that okay? I mean, if the result of the integral doesn't make sense, then just do the derivative to check. What's the derivative of e to the negative lambda x with the minus? Well, by the chain rule, exponential function doesn't change under derivative, but you take the inside function, pull it outside, and differentiate. What's the derivative? X just differentiates to 1, right? So you end up with lambda times e to the negative lambda x. So it's exactly the same as this thing. In other words, if you have anything here, the reciprocal of this number will appear in the front. That's how you do the integral. Okay? So you do that integral, and once you've completed this, then you just read off like this. 1, 2. Those are the integrals. That's a lot faster than doing the traditional integration by parts. Okay? So you have negative x times e to the negative lambda x, plug in infinity and then 0. And then the next one is minus 1 over lambda e to the negative lambda x. Right, and then you plug in infinity and 0. So when you plug in infinity here, lambda is always positive in here. It can't be negative because probably a distribution function cannot give you negative values. So that being here means lambda has to be positive. And if you have e to the negative positive times some big number, that's a very small value, right? It goes to 0. Remember, e to the negative infinity is 1 over e to the infinity. And e to the infinity is huge, so that must be 0. So when this goes in here, it gives you 0. And it goes to 0 quicker than this going to infinity. So overall, it'll be 0. When you plug in 0, 0 times anything is 0, so that's going to be 0. When you plug in infinity, again for the same reason, it's going to give you 0. And when you plug in 0, minus negative 1 over lambda times e to the 0th power gives you 1 over lambda. Okay? So, now how do you understand this geometrically? Well, think of it like this. If lambda is 1, it's just e to the negative x. Isn't that right? So the graph is something like this. Now if lambda is bigger, then let's say lambda is 2, then it starts from 2, but it goes down to 0 much faster. So if lambda is 2, this is lambda equals 1. If lambda is 2, it goes like this. It drops down much quicker. And if you look at the average value, you can see that the average value will shift towards to the 0. The quicker it decreases, there's less chance that you will get a high value. So if you have something really huge and goes like that, it's very hard to get a value that's big, right? So your average is going to go down. And that's exactly what this result is saying. If lambda is big, then you have 1 over a big value which is small. So it is in accordance with the graph that you see. It's good to try to rationalize your answer by thinking of what's happening to the graph. Okay, so that's the average. Now let's try to think about the variance. So variance is e of x squared minus e of x squared. And you just have to find e of x squared, which is, well, it's the same story, just like this one, except this time you integrate against x squared. So x squared times lambda e to the negative lambda x dx is what you have to integrate. Okay, let me give you some time to try. So you have x squared, 2x, 2 and 0, plus, minus, and then lambda e to the negative lambda x integrates to negative e to the negative lambda x, integrates to 1 over lambda e to the negative lambda x.
Then you gotta do one
You
more.
have minus 1 over lambda squared e to the negative lambda x.
Square. Yeah.
Because every time you integrate, 1 over lambda comes up. Negative 1 over lambda.
Yeah.
The reciprocal of this number comes in front, so you end up with that, okay?
I thought it was.
So that's going to give you the integral,
Yeah.
which is x squared negative e to the negative lambda x. And then, what's the next one? This one.
Yeah.
Minus 2x over lambda e to the negative lambda x.
Yeah. Then
And
plus.
this one, minus 2 over lambda squared e to the negative lambda x. You plug in infinity and 0. Anytime you plug in infinity to these things,
There's 0.
they're 0.
And that makes.
The minus, and then when you plug in 0, the ones with x's will be 0.
Yeah.
So you have negative 2 over lambda squared as the result, which
So,
is
yeah.
2 over lambda squared, right? But then we're looking for the variance. What's the variance? This is e of x squared, which we just computed, minus e of x squared. We computed this a moment ago, right? That's 2 over lambda squared minus 1 over lambda squared, which is 1 over lambda squared. So that's the answer.